Hi, welcome to video 4.5D. This is still integration by substitution, but there's an extra little twist here. There's going to be an extra variable left over. Okay, so they don't call it that, but I call it that. Okay, so if we look at numbers 67 through 74, let me get rid of that. So 67 through 74, in 4.5. Right here. Okay, so it says find the indefinite integral by the method shown in example 5. So you'll notice what happens in every single one of these is we're going to have a leftover variable. So for example, let's say in 67, you'll let u equal x plus 6. The derivative of x plus 6 is 1 dx, so I have this extra variable here. And I can't pull it out on the outside, I can only pull constants. Same thing here, your derivative of 1 minus x would be negative 1 dx, so x squared is extra. Here, the derivative of 2x minus 1 would be 2, so I've got this x squared that's extra. Here you'll let u equal x plus 1, and again you'll have all kinds of extra things. Okay, same thing here, derivative is 4, you got an extra, derivative is negative 1, you got an extra, derivative is 1, you got an extra, derivative is 1, you have an extra. Okay, so here's how we deal with that. You can't, what I mean by you can't use the shortcut is you can't try and do this one in your head. You actually are going to have to write out let u equal. So as usual, we'll let u equal the contents of the radical. If u is 2x plus 1, du is 2 dx. It's at this point you realize I can introduce the 2 and counteract with the half, but I'm left with this extra variable. So what you do is you go back to your u equals and you isolate that extra variable. So x equals u minus 2 over 1. And then you have to rewrite it all in terms of u's. Now I'm purposely going to I'm going to put the dx over here. I'm going to introduce the 2, counteract with the half to have the du. This, of course, is my u to the half. I'm going to stick this extra variable in here. What I have at this point is 1/2 integral u to the half. Remember my x was u minus 1 over 2, and my 2 dx is 2u. At this point, what you're going to do is pull out that extra 1/2, so you have a quarter, and you'll be left with u to the half times u minus 1, which you will distribute. You will then integrate with respect to u. After you've done that, you'll replace your u's by 2x plus 1. Here's another one, number 70. If you let u equal 2 minus x, the derivative is negative 1, which all you have to do is introduce the negative, counteract to the negative, but I'm left with this x plus 1, so I have an extra variable. So I go back here, isolate x is 2 minus u. I have negative integral 2 minus u plus 1 times the square root of u du, which is 3 minus u times u to the half, distribute, integrate, etc. Don't forget to change it back into x's. Same thing here, let u equal the contents of the radical, derivative is dx. You'll notice I have this extra variable here, so I'm going to let x equal from here u minus 4. So I replace, I have 2 times u minus 4 plus 1 over u to the half du. Distribute on top, I get 2u minus 7 over u to the half. Personally, what I would do is split it up because that's a monomial. Or you could bring the u to the half on top, make it u to the negative a half, multiply through, that's to the 1. You'll get the same thing, which is this down here. Integrate that in terms of u. Don't forget to replace u in terms of x. Okay, so now we're moving on to what happens when you have a definite integral with an extra variable. And that's going to lead us into another discussion. So again, let u equal the contents of the radical. Derivative is 2 dx. Uh-oh, extra variable. So what we're going to do is we're going to isolate x here and get u plus 1 over 2. Now here's the deal. When you have the integral and you have a dx, that automatically implies that this refers to x equals 1 and this refers to x equals 5. Once you replace them all in terms of u's, you cannot write from 1 to 5 because that's for x goes from 1 to 5 and you don't have x's here. So what we do is we can drop them. Okay, so simply ignore them. And let me show you how to do that down here before I get into this. Okay, so just drop the limits of integration and then integrate this. Now this, of course, I multiply by 1 other reciprocal. I end up with u plus 1 over 2u to the half. Pull the 1/2 out, I get a quarter. You can either split it up, as we said before, or bring this u to the half up. Integrate with respect to u, put it all back in terms of x. Now that it's back in terms of x, now you can reintroduce the fact that the original question was from x equals 1 to x equals 5. And now that you have it in terms of x, you can do that. So you plug in the 5, you plug in the 1, you subtract, you get 16/3. Okay, now, there is another way to do this, and do not stop listening at this point, because there are questions on the AP exam that specifically check to see whether you know how to do what I'm about to do. And it's actually a time saver, okay? What you do is this. Once you get it in terms of u, what you can do is say, you know what? Let's rewrite this x equals 1 to x equals 5 in terms of u, because we know u is 2x minus 1. So it was from a top limit of integration of x equals 5 and a lower limit of integration of x equals 1. If I plug x equals 5 into this expression for u, x equals 5 implies u equals 9. If I plug 1 into 2x minus 1, that means when x equals 1, u is 1. I can now put the limits of integration because they are in terms of u, and this is called changing the limits of integration. Once you do that, the beauty is you won't have to put it back in terms of x anymore. You can leave it in terms of u because you have the correct limits of integration in terms of u. And when you simplify that, you'll get the exact same answer. Okay, so here's another example. Let u equal the contents of the radical, derivatives dx. I have an extra variable. If I isolate x here, x is u minus 2. So that will mean x squared is u minus 2 squared. This is my u to the third. That's my du. Now I'm going to change those limits of integration over here. Because I know that u equals x plus 2, and because I was going from a lower limit of x equals negative 2 to an upper limit of x equals 6, if I plug 6 into this u equals x plus 1, I'll get u equals 8. If I plug negative 2 for x into here, I'll get u equals 0. So the equivalent of x equals negative 2 to x equals 6 is u equals 0 to u equals 8. And now I don't have to go back to x's ever again. In this particular case, there's no point in letting letting v equal u minus 1. You'll have another extra variable. It's actually easier in this case to expand this and then distribute out the 1/3. When you're done, though, you will leave it in terms of u because you have u equals 0 to 8.